Hello, my name is Nicholas and welcome to another update for the Space Game project. Since the last video I've been working on planning out how I want this game to progress and where I want to take it. I've spent a lot of time working out how I want most of the mechanics to work, but the major changes that I've made have mainly been to do with the project base and the movement system. The first major change is that the simulation I'm showing you currently is all working off a brand new project base. That means that I took a lot of the code that I needed and a lot of the classes and resources out of the old project base, which was the CGBC trading simulator, took all those resources out, built a new project base, plugged all of those classes back into it, and tidied up a lot of unnecessary elements like the trading system or the bounty and loot system. The other major changes have all been to do with the movement system and how the ships move around the world and find their destinations and positions and so on. The main change that's been made to the movement system is that it has been changed from being a frame-by-frame update system, which is what is fairly common for most games in the industry, to a keyframe system. And the difference is this. If you've got an object on your screen and you're using a frame-by-frame update system, what happens is that object has a position that it stores and it also has a velocity that it knows it's moving in. So every frame, the game computes the object's new position based on that velocity, where the frequency that this position is updated is based on how often the game can update itself, which means that for most games it would be around 60 times a second. One thing to note about this system is that we don't actually know where the object's going to be that far into the future. We compute the object's position when we get to that point in time based on its velocity, which means that we only have a very small area that we can predict where the ship will be or where the object will be in the future. If we compare this to a keyframe system, the main difference is that objects in a keyframe system don't have a velocity. What they have instead is a graph that maps out their position across time. So we know that at a certain time the object might start here, and we know that at a certain time in the future the object might be here. And so what we can then do is smoothly, using the graph, map out the transition of that object from its initial position to its final position by following the graph which stores all of its positions in relation to time. What this means is that not only can we map a single point ahead, but we can in fact map multiple points into the future on this time position graph. The way these graphs work is that on one axis you have position and on the other axis you have time. On this graph we can then plot the position of the object in relation to time. And what we'll get is a series of points which map the x position of the object onto time, and using these points we can see whether the object is at rest, whether the object is moving in a linear fashion, whether the object is accelerating as represented by an exponential graph, or even whether the object is decelerating represented by a similar graph. And we can mathematically compute the exact position of an object at any time simply by cross-referencing the time and the equation for whatever part of the graph we're looking at. If we compared this to a frame-by-frame system, we would have the object's position here and here and here and here as the game updates, but we wouldn't be able to know where the object was in between these updates. And these updates wouldn't be tied to any specific time, meaning that the game could lag and become unsynchronized. One really great thing about this sort of system is that this can be used to map anything. This can be used to map an object's x position, an object's x and y position, an object's health. This system could even be used to store events, which, rather than being stored as a series of points, could be stored as a number of time values which would denote the start and the end of a particular event. An explosion, for example, might be a good use of this, where regardless of where the updates fall for the game on the timeline, knowing where the event was caused and where it finished, the game will be able to draw the corresponding part of the explosion. Regardless of what data the graph stores, there is a number of different ways that you could interpolate between the values that you're given. The first method is something which I call a stepped method, whereby the value is always the value of the preceding keyframe. In this fashion, the graph resembles a set of stairs which maintain a constant value and only change at the point where a newer value is implemented. Such a graph could be used to represent the health of a ship. For example, if we invert this graph, we could see that a ship might be on full health until an event such as taking enemy fire occurred. He would then drop down an amount equal to the damage dealt to him, and then he would be on this new health value until such an event occurred again. Another way to connect these points would be with linear graphs, which would simply be straight lines connecting the points like so. This could be used to smoothly change between different values, such that over time the rate of change is always constant. We could also use exponential graphs between these points in such a way that whatever change is occurring is initially slow and then rather quick. This sort of graph is well suited to acceleration of ships for movement, where initially their speed is very small, but as they accelerate their speed becomes greater and greater. And of course the opposite of an exponential increase graph would be an exponential decrease graph, whereby a large change becomes lesser and lesser over time, and which could be used to map spaceships decelerating, where they're coming into the graph from maximum speed and then slowing down until they come to rest. The most important thing about all these different graph types is that they are not mutually exclusive, and within the one graph you can in fact utilize many different types of interpolation to achieve a range of complex movements. Meaning a single graph could have both linear sections, exponential increase sections, exponential decrease sections, and even stepped sections. With this new movement system implemented, ships can accelerate and decelerate over short distances, meaning that they don't actually reach their maximum speed, but go as fast as they can before they need to slow down to stop. They can accelerate to reach this maximum speed, cruise until they need to decelerate to reach their destination, and then slow down. And they can in fact receive orders while they are mid-movement, which redirect them, and you'll see that they conserve a small amount of their momentum while they're turning. What this means is that for particularly fast ships, while they can reach a high speed, they won't be able to simply turn around instantly. They will in fact have to decelerate and then accelerate again in their new direction. If we take a single ship which has a very slow acceleration and deceleration speed, but which has a very high maximum speed, and give it an order to move across the stage, we will be able to see the acceleration, cruising, and deceleration parts of the ship's movement. What we can also see is how the ship's momentum is conserved when it is given a new order which takes it from this path. And finally, we can show how a ship which doesn't have the room to make its maximum speed will still move as fast as it can within the space it has allotted. Moving from a frame-based system to a keyframe-based system has a number of foreseeable benefits. Firstly, the simulation becomes much more precise, because rather than having to guess the future position of the game world, it actually knows the future position of the game world because it has mapped it out mathematically beforehand. Another foreseeable advantage is the fact that the amount of data required to network the game to make it multiplayer is vastly reduced. Rather than having to send updates about every position that the ship inhabits, the game can simply send information about the start and end points that a ship moves through. And the final sort of big benefit which I can see is that because every unit will then store all of its information about itself on a time graph, that information is there and immediately available should we need to work on creating save game files or even creating replay files. Or one very interesting thing that we can do with this information is we can actually reverse the direction that the simulation plays and have the ships move backwards through their position graph, reading off all the values in reverse order. And what this means is because we have all of this information already saved in our simulation, When it comes to saving replay files, all we need to do is copy all of these graphs, and it becomes almost like an animation that you can then watch through. Another interesting thing that this allows for is the ability for the viewer to take over from the replay at any time by simply changing the time to moving forward, cutting the graph where the user wishes to intervene, deleting all of the information in front of that point, and simply running the simulation from that particular location. Future plans for the movement are if a unit has a direction of travel and is then given a new direction of travel, either after it reaches its destination as a queued order or as an interrupt for what would have been a continuing movement path, rather than having the unit simply stop and come to a complete halt at this point, I would like to actually have the units curve around this point, making a smooth cornering action, meaning that they can also maintain a small amount of their momentum. The amount of momentum that they maintain could be determined by measuring the angle between these two directions, but also by having each ship have a maneuverability statistic which determines how much speed it loses while turning, meaning that smaller ships would be much more agile and could maintain a great amount of speed around the corner, whereas much larger ships would have to slow down much more. These plans aside, what I aim to work on next is making sure that all of the order system is still in place. The ships still have pilots attached, the pilots still maintain the orders. Need to go through and make sure that all of the different order types are still viable. Patrol orders, queued orders, particularly attack, move and follow orders, those types of orders where a ship's final position is based on the position of another object in the game. I foresee there could be slight problems there, but because we're basing all of this off the idea of a graph, the worst that can happen is on the graph we simply have data points every 60th of a second every time the game updates and the ship is given a new position for it to move towards. So that's about it for this update of the Space Game project. If you guys have any comments or questions, leave them in the section down below. If you guys have enjoyed this video, give it a like. If you would like to see more videos or keep up to date on this or other projects, check out my channel and subscribe. I hope you guys have enjoyed this video. I'll see you next time.